All right, we're finally ready to work some full trig sub examples, which I know you've been looking forward to. If you did not watch the previous two videos about what to do at the beginning and what to do at the end of these problems, I would definitely watch those first because that's where most of the confusion comes from. If you just jump straight into the trig substitution examples, I'm going to be going pretty fast through some stuff that I cover in depth in those because the trickery is not in the middle. The really tricky stuff is the first step and the last step, and that's what those videos are about. So this video is almost unnecessary if you watch those because this will just be kind of putting it together, stuff that we've already covered quite a bit. Alright, so here's an example. Now if I were you, I would not use trig sub on this one. Why not? Because you could use u substitution. Just do a regular derivative, a regular integral using the power rule. Because we'd have u to the negative 1/2 power, our u would be x squared plus 9, which means our du would have an x in it. Oh, and look, I've got an x to work with. But hey, since we're in the trig sub chapter, let's do some trig sub. So I think we've established this point. If you watch that first video, we're going to need a 3 here because 3 squared would give us a 9. And then this is going to be what? I believe tangent. Alright, so dx is going to be 3 secant squared theta. So up top we got 3 tangent of theta. Downstairs we've got square root of 9 tan squared theta plus 9, and then my dx is this whole thing, so 3 secant squared theta d theta. Alright, so now downstairs, 9 tan squared plus 9 is going to give us 9 secant squared, if you know our identities, and of course square root of that is just going to give us 3 secant theta downstairs. So at this point we've got the integral of this 3 cancels this 3, so we've got tan theta, and then the secant theta cancels one of these. So we've got the integral of tan theta, and we've got a 3 right there. Then we got a secant theta, and we got a d theta. Well, what do you know? That happens to be a really easy integral. It's just the integral of secant times tangent is just secant. So this is 3 secant theta plus c. So you can see how the hard part was definitely making the substitution, like picking what to substitute, and then doing all the canceling and everything. The actual integration itself, the step we've been skipping to this point, was really easy. And then I just need to now do what we did in the second video, which is get from my thetas back to x's. So since this is tangent to the secant, I have to draw my triangle. I would just draw a triangle every time if I was you. So first of all, we get the sides of the triangle just from the substitution. And again, this is what the second video was all about. So tan theta, if I just rearrange this and solve for tangent, I get that tan theta equals x over 3. So that means the side opposite theta is x, and the side adjacent is 3. And then this side is square root of x squared plus 9. Alright, so secant, the secant of theta is going to be hypotenuse over adjacent, because it's the flip of cosine. So cosine is adjacent over hypotenuse, secant is hypotenuse over adjacent. So that's going to be times the square root of x squared plus 9 over 3 plus c. 3's cancel, so we just end up with square root of x squared plus 9 plus c. Alright, so as you can see, 90% of our time was spent doing the stuff we did in those first two videos. Actually integrating it was no problem. Now sometimes the integral is ugly. Like if it was a sine squared theta, well, you're going to have to use your power reducing formula and stuff that we cover in the trig integrals section. So trig sub and trig integration are two separate sections, right? Trig sub is where we're taking a perfectly normal x thing and sticking in trig functions instead of x in order to get rid of some square roots and whatnot. Trig integration is just when the problem they give you has a bunch of sines and cosines and secants and stuff, and just what to do about different powers of sine and different powers of cosine and all that kind of thing. But that's a different video. These problems are pretty much always have an easy beginning and an easy end with the triangle. And it's just a question, that integral in the middle could either be easy or hard depending on which particular problem you're looking at. But so trig sub though, not too bad usually. Alright, so this is one of those problems where if we have our arc sine and arc cosine and arctangent formulas memorized, this is one of those. But since I don't remember it, I'm going to have to use trig substitution. So this one's going to be, since we have a number minus x squared, we're going to do the square root of 16 is 4. And then this is going to be a sine substitution. And if you don't know why I did that, watch that first video in this chapter. And therefore my dx is going to equal 4 cosine theta d theta. Alright, so let's make the substitution. Dx is 4 cosine theta d theta. And downstairs I've got the square root of 16 minus, and then if I stick in 4 sine theta here, I'll get 16 sine squared theta. Alright, so downstairs where the magic's going to happen, obviously. 16 minus 16 sine squared gives me 16 cosine squared. And if you don't believe me, watch that first video. Square root this puppy, because I'm still under a square root, so you square root this, and you end up with 4 cosine theta d theta. Alright, so, wow, that's interesting. Oops, I'm sorry, that d theta does not belong there. It's just 4 cosine theta. Alright, so, here's something funky. Right now I have got 4 cosine theta d theta upstairs, and downstairs I've just got 4 cosine theta. How the heck did that happen? Wham wham, there's just the integral of d theta, which is just theta plus c. Now I covered what to do about this in the second video of this chapter, but basically there's no triangle to draw here, right? Well, I mean, we can draw the triangle, but there's no SOHCAHTOA to do backwards. So my original substitution was 4 sine theta, which means sine theta equals x over 4. Just divide both sides by 4, we get that sine theta equals x over 4. So the sine is x over 4, based on the angle being right here, opposite and hypotenuse. And that makes this side whatever, square root of 16 minus x squared. Although we don't actually need that for this problem. But so now here's the question. What the heck is theta? If this had been a cosine theta, great, I would just put square root of 16 minus x squared over 4. I could do SOHCAHTOA. But this is not a trig function, it's just theta. So it turns out the big trick is that means you're dealing with an arc sine or an arc tangent or something. And since we started with sine, you're going to want to do an arc sine. So this is simply theta equals the arc sine of, sine would be x over 4, and then just keep that plus c. So it turns out that is our answer. It didn't quite really equal theta, I guess. So our answer, theta plus c, is just arc sine x over 4 plus c. And I covered this exception a little bit in the second video as well. Alright, so why is this a burn example? Well, we should just use u sub on it, right? This would be u to the 1/2. My u would be x squared plus 3, therefore my du has an x in it. Yay, that would have worked fine. Let's try doing trig sub and see if we get the same answer. So, I've got something plus something, so I believe we got x equals, I'm going to go tangent. Yeah, okay, so square root of 3 tangent of theta, which means my dx is square root of 3 secant squared theta d theta. Alright, let's see what happens here. So we got square root of 3 tan theta times square root of 3 tan squared plus 3 times dx, which is square root of 3 secant squared theta d theta. Alright, so this thing, this whole mess 3 tan squared plus 3 is going to be 3 secant squared, so we get square root of 3. Sorry, no square root. Just square root of 3, but then secant theta is not under the square root. Alright, so out of this mess, we've got square root of 3 3 times, so that's 3 root 3. Then we've got a tangent and a secant squared. So we've got tangent, write this properly, tangent theta, and then we've got secant cubed theta. Alright, and this is all being integrated. So this is one of those tricky ones. How do you integrate powers of secant? Well, it turns out the trick on this one, and I'll cover this in the trig integral chapter as well, but the trick here is to split up this secant cubed into a secant squared and another secant. So, and the reason for that will be obvious in a second. So what I'm going to do is I'm going to make a secant squared, and then I'm going to have the other secant that I didn't use just now. So I've still got 3 secants, 1 here and 2 here, tan theta d theta. But the reason for that is that if my u, now we're just doing u substitution. So u equals secant theta, so that's just u squared, and then this is going to be my du, because the derivative of secant is secant tangent. So that means I'm really just integrating 3 root 3 times the integral of u squared du. Which is going to be 3 root 3 secant cubed theta divided by 3. Alright, pretty cool. So now the question is, how do we switch back from theta to x? So I'll draw my triangle here. Theta. So tangent theta was x over root 3. Does that make sense? Yeah. Divide both sides by root 3. We get tan theta equals x over root 3, which means that this is square root of x squared plus 3. Alright, so I've got my root 3 I just keep, and then I need secant cubed, and secant is going to be square root of x squared plus 3 over root 3, and this was cubed. Alright, so when you simplify all that out, you've got square root of 3 times x squared plus 3 to the 3 halves and then downstairs I've got square root of 3 cubed, which is 3 root 3. The root 3's cancel, and that just leaves us with 1/3 x squared plus 3 to the 3 halves power plus c. And I can't believe it worked out, but that is in fact what you would have gotten with the power rule and u substitution. So if you'd done the power rule, you would have got, you would have done u equals x squared plus 3, and therefore your du equal 2x dx. So you need a 2 here, and therefore you put a 1/2 out front, and then you end up integrating this, and you get that same answer, or at least this is the answer I got when I integrated with u sub prior to making the video. So, wow, I'm amazed that worked out. I don't know if you saw me pause there, but I really didn't think this was going to work out in the middle there, but it did. Awesome. All right, so why is this one a super tricky example? I'll show you. We're going to have to integrate secant, which is a really tricky integration to do. All right, so as far as what to substitute, this is one of those ones that has something squared minus 9, so that's going to be a secant substitution. Yep, so x equals 3 secant theta. So our dx equals 3 secant x, secant theta, tan theta, d theta. Okay, so we're ready to substitute, guys. Alright, so dx will be my numerator, and that is 3 secant theta, tan theta, d theta, over square root of 9 secant squared theta minus 9. Alright, we're looking good so far. So the 9 secant squared minus 9 just gives us 9 tan squared. And then we take the square root of that and we end up with 3 tan theta downstairs. Alright, but this tangent is going to cancel this tangent, and this 3 is going to cancel this 3. This happens a lot in these U-sub problems. So what we ended up with was the only thing left is secant theta d theta. Now here's where this thing gets tricky. This looks like a straightforward integral, except if you think about it, none of your integral formulas cover the integration of secant theta. You know how to integrate sine or cosine. Secant squared would be a tangent. Secant tangent would be secant, but secant doesn't integrate to anything straightforward. And that's unfortunate because that means we're going to have to do something tricky. And it just turns out there's an algebraic trick for this, which is we're going to multiply secant theta times, and we'll just throw it over a 1 since we're going to turn this into a fraction. We're going to multiply it by secant theta plus tan theta over secant theta plus tan theta. Now you're probably looking at that and you're going, if you've never seen this trick before, you're thinking that is the craziest thing I've ever seen. And you're right, it is. We added a tremendous amount of junk for the sake of integrating something. But I'll show you why it works. I mean, you'll be surprised it works out pretty nice. So we've got secant squared theta plus secant tangent. You know, those have thetas, obviously. And then the denominator is just secant plus tan theta. And of course there's a d theta in here somewhere. So this looks like a giant mess, but here's what's crazy. We can now do a u substitution integral. This right here, let's pretend for a second this was our u. Our du would have to be the derivative of that, right? The derivative of tangent, derivative of secant is secant tangent. Oh, look at what I have there. The derivative of secant. And the derivative of tangent is secant squared. So shockingly, after turning what looked like a simple problem into this ludicrous mess, we've actually created a situation where it integrates smoothly. This is just the integral of du over u, which you might be thinking, hey, that's just the integral of u to the minus 1. And then you use the power rule and you get u to the 0, and then you're like, oh my gosh, that's it. No, it's a natural log, right? So we're always on our toes whenever we see 1 over u, because that's the natural log. So that's just the ln of u. And of course, in this case, that'd be the ln of this crazy thing, secant plus tan theta. And then when we switch back in, got to draw our triangle. Secant theta is x over 3, so that's x over 3, which means this side is square root of x squared minus 9. So this is going to be the ln of x over 3, because secant theta is x over 3, and then tan theta is 1/3 x squared minus 9. Alright, that is completely crazy, but as you can see, the difficulty from these problems comes from that integral in the middle. Usually the trickiness, though, is the stuff we covered in the previous 2 videos. So if you didn't follow this video, go back and watch those because they're awesome.